looked into the compressive strength and relevant issues related to compressive strength in the previous lecture. Now, we should look into other mechanical properties, and today we shall look into tensile strength, fatigue strength, and impact abrasion resistance of concrete, right. So, tensile strength we will look into first, tensile strength of concrete, and the general outline of our discussion today would be tensile strength. Now, we look to tensile strength in two different weights. One is called flexural strength, other is split test. We will describe this, and this relationship with compressive strength, that is what we will look into. Then individually we will look into fatigue strength, impact resistance of concrete, and abrasion and bond strength. Now, let us see why do you need at all the tensile strength of concrete. You see, concrete generally we exploit its properties in such a manner, we exploit in such a manner that we rely mostly on its compressive strength and least on its tensile strength, because we know that it is weak in tension, and therefore we put reinforcement in reinforced concrete structures, or we pre-stress them for that purpose, so that it can withstand certain amount of tensile loading. However, in some cases we may have to still rely on the tensile strength of concrete. The examples are, for example, where shrinkage cracks comes in, shrinkage cracks, to arrest those shrinkage cracks, or shear cracks, or differential movement cracks, or cracks due to any other reason. So, whenever such cracks come in, to resist such cracking, we have to rely on the tensile strength of concrete in many cases. Now, there are examples where these are certain structures are designed for tensile strength of concrete. For example, dam under earthquake excitations, pavement slabs, airport runways. These are designed on the basis of tensile strength, direct or flexural tensile strength as the case may be. Therefore, we got to know the tensile strength. And it can be seen that tensile strength can be related to compressive strength, because as we have understood from the failure mechanism of concrete in compression, after all, even in uniaxial compression, concrete fails in tension. So, there could be some sort of an empirical relationship, correlation might exist between the two, and in fact, they really do exist, and we relate it that way. Okay. So, that can be understood from the failure envelope of concrete. If you remember, we talked about biaxial testing of concrete. So, when we look into the biaxial testing, for example, if this axis shows the tension in a given x direction, and this is tension in the y direction, other direction, biaxial situation we are looking at. This is the compression, and this is also compression, right. So, this is the neutral point where there is no stress, this side is the tension, this side is the compression. So, if I call this plus, I will call this minus, this is the compression, tension in the y axis, and compression in the y axis goes along this direction. This gives us the failure envelope. That means, at this point when there is only one compression, it is a combination of load, because it is a biaxial loading situations, and the failure envelope shows under biaxial condition how concrete fails. Now, this one would mean, this point would mean that I have compression along this axis, x axis up to this point, and there is no tension or compression along the other direction. So, this point represents uniaxial compression, and you can see this value is 8 K, where K is this value. Now, what does this value represents? This value represents uniaxial tensile strength along y direction, and this is same as the uniaxial tensile strength along this direction, because here the stresses along x direction is 0, whereas in y direction it is K. So, this envelope represents the failure envelope. When you have combination of tensile and compressive load on both directions, a biaxial situation, both the direction, that means you might have compression along this direction, in the other direction you might have tension or compression. So, that is the biaxial, biaxial situation. For example, if this is your sample, if you have compression, so and maybe tension along this direction, or you might have compression along this direction or you might have tension. So, combinations of this situation. So, this point represents no tension compression along this direction. However, you have a pure tension along this direction, okay. So, uniaxial tension, and this value is K. This value is also K, and this is rectangular. In fact, under combination, when you have biaxial tension, that's also is, this is K and K both together fails here. So, if this is K, uniaxial compression is 8K. Similarly, along this direction, when there is no stress in the other direction, when there is no stress in x direction, only y direction I have pure compression, this is 8K. So, compressive strength is 8 times of tensile strength, and therefore, there seems to be a relationship. It is 8 times is a compressive strength, as shown by this failure envelope study, experimental study. So, there is some relationship between the compressive strength and tensile strength, and this will be further, we will look into such relationship. Now, how do we test for tensile strength? It is difficult to measure tensile strength directly, because the specimens, initially they were tried like this. Initially, one would have, people have tried briquette test. What is called briquette test? You have samples, and like this, samples like this, like mortar or concrete briquette test, and this is the sample. This is the sample would look like this, and you will grip this here and grip this here and try to pull. Now, what would happen in such situation, this gripping was rarely proper, and the failure would always take place along this direction, along the grip itself, because of satisfactory gripping was difficult, and therefore, direct tensile strength was difficult to measure. It was quite difficult. So, this test is not now relied upon by any code or anything, rather indirect methods are used for measurement of tensile strength of concrete. For example, after all, most of the cases we rely, tensile strength of concrete is required possibly under flexure, under bending, if you may recall, under the bending situations, when a beam is loaded, in some form, it bends and the bottom is under tension. So, when a reinforced concrete beam or any beam is bending, the bottom is under tension, and therefore, flexural tension is an important property that we would like to know. So, one of the ways is to test a beam, and this test is known as modulus of rupture test. We will look into the test in more details in a short while. A second way to test is through what is known as split tension test, and is also an indirect test. So, there are no direct tests, there are two types of tests. One we call as modulus of rupture test, which is nothing but strength in flexure, and second one is split tension test. Let us see the first one first, the modulus of rupture test. This is what it would look like, this is what the modulus of test specimen would look like. For example, you will have 2-point loading. Commonly used is 2-point loading. This is one point, this is another point, and these points are, if this length is 3d, this distance is d, as you can see this distance is d. So, you have two roller supports here such that it is simply supported, and you have the load coming from the top of it, a single point, through a single point, you might be loading it like this using a single point P, whereby it will get divided to P by 2 and P by 2 again. By using roller, you are ensuring that it is actually point load. So, this is point load and point support and point support. So, a purely simply supported system with 2-point loading. This is depth is D, this is B, okay, usually 10 by 10 by 50 centimeter is used in IS code, 10 by 10 by 50, with this being 40. Here of course, it could be 4D or 5D. So, this is about 13 in case of Indian standard situation of IS 516. So, 13 into 13.3 and overall is 50 centimeter is the overall span. So, this is simply supported. These are supporting rollers. This allows for rotation. So, makes it purely simply supported. There is no restraint here, no horizontal reactions will be available, only vertical reactions of P by 2 would be available. So, you can see that P load, P by 2 uniform load is applied here, and P by 2 reaction should be obtained here. And if we look at its bending moment diagram, this will look something like this, because we are interested in finding out how much will be the load carrying capacity, right. So, this is the bending moment diagram, as you know, because P by 2 here, the reaction should be P by 2, and the bending moment diagram would look like this, because P by 2 it will be 0 here, simply supported system, it will be 0 here because it's a simply supported system, it will be 0 here because it's a simply supported system, and as you can see, the bending moment maximum will be P2 into L by 3, because this is P by 2 and this distance is L by 3. So, maximum bending moment is P by 2 into L by 3, and same thing from here if you calculate out. So, maximum bending moment will be PL by 6, and how do we find out the bending stress? We find it out as F equals to m over z and PL over BD square. This is what will come, because we know the Z for this section would be BD cube by 12 for a rectangular section. We are using of course B and D in general terms, but usually they are same. So, 10 centimeter, both are taken as same. In any case, it is BD cube by 12, as you know, for a rectangular section. The I inertia, moment of inertia is BD cube by 12 divided by D by 2, because we are interested in the maximum extreme fiber stress. So, this is D by 2. So, BD cube by 12 divided by D by 2 would result in BD square by 6 and PL by 6. So, finally, the extreme fiber stress would be given as PL by BD square. So, if you know the P and the failure P max, if you know the failure P, where P is the overall load applied at this point, So, if you know P, then the modulus of rupture will be the flexural tensile strength will be given by PL by BD square. This we also call as modulus of rupture. Now, you see two things one must notice from here. First of all, shear force in this zone will be 0. Shear force is 0. No shear force in this. So, if you draw a shear force diagram, a shear force diagram, you will possibly draw it something like this, shear force diagram. So, there is no shear force here, no shear force in this zone, it is pure bending, pure flexure. Also, this is spanning over a distance of d. The maximum bending moment is spanning over a distance of d. Now, we could have also used single point loading. So, if you use single point loading, obviously shear force would not have been 0 in any part of the section. Not only that, the maximum bending moment would have been there only in one place, only in one point, one single point. Now, failure could take place in that point or may not take place in this point. That would depend upon whether there is a weak point at just below the load or not. If the weak point is somewhere else, it will fail there. So, which means the probability, it will depend upon probability of finding the weak point at the maximum load point, or just below the load point where load has been applied. Now, this tend to give you much higher strength, as we shall see. So, that is not the best way to do it, and that is why most of the code adopt this. There is, since you can eliminate out shear from here, shear force from here, shear force from here, and also this is pure, this is bending here, and you have a span. So, 2 point loading is preferred over 1 point loading. Okay, and you can see that in fact people have tried to do test with 2 point loading and 1 point loading, and 1 point loading tends to give you always higher load. 1 point loading always tends to give you higher load, right. So, single point loading gives you always higher apparent tensile strength, flexural strength, whereas 2 point loading gives you apparently low tensile strength. Okay. So, this is one kind of test that we do, and this test we call as modulus of rupture test. Right. Now, this test, if you remember that we assume a specific kind of stress distribution in the calculation when we have used the linear elastic bending theory, actually we have assumed a stress distribution, rectangular stress distribution, simple triangular stress distribution, triangular stress distribution. We have assumed a triangular stress distribution in calculating out F equals to P L by B d square, that we have calculated out, because we have used m by z equals to f, etc., etc. If you remember, that uses a triangular stress distribution, because we are assuming the linear behavior of the material, but in actual concrete the behavior is something like this. Your concrete beam, at the failure the stress diagram is something like this, in the compression and the tension zone it is something like this, and this value is actually lower than the what we have calculated. So you can see that we have estimated the tensile strength as this, but actually it is this much smaller. So we are overestimating even the flexural tensile strength, because we are using the modulus of rupture, which is calculated on the basis of triangular stress distribution in compression as well as in tension, and therefore we overestimate. This is one problem. A second problem, or not a problem really, because we understand this, so it's not a problem, but this is the actual, it is a deviation from the reality. Second aspect is that in such tests, this extreme fiber is subjected to maximum stress, whereas all other points, this point, the neutral axis, let us say, all other points here is subjected to lesser stress than this. So now this is the only point which is subjected to maximum stress. Now supposing I have, there are some strong points here, it is not, the weak plane is not here. So this fiber, the crack doesn't propagate, of course the crack would propagate, you can see the other direction, the crack would propagate like this. So the crack doesn't propagate, or it gets stuck somewhere by an aggregate or something of that kind, then it will again tend to give you higher load. The volume of the concrete which is subjected to the tensile stress is relatively less, because this is subjected to maximum, rest all are subjected to lesser and lesser stress, whereas this side is purely in compression. So this is another reason why modulus of rupture would tend to actually overestimate, right. So overestimate the strength. So you can see that this is true strength is somewhere here and calculated strength is bigger. So 2-point loading, so therefore summarizing this discussion just now, I have talked about 2-point loading ensures pure bending without shear in the central 1/3 span. 2-point loading produces maximum moment between the loads, thus more area is exposed to maximum bending moment than 1-point loading, hence lower apparent modulus of rupture. So when we compare between 2-point loading and 1-point loading, we find that 2-point loading gives us lower apparent modulus of rupture. But calculation of modulus of rupture assumes triangular stress distribution, actual stress differs, some other points we will discuss again a little bit more later on. So henceforth it has been observed that modulus of rupture is greater than the next test I will talk about, that is called split tension test or direct tension results if they are available. But as I told you, it is difficult to obtain direct tensile strength results. So in any case, MOR gives you higher value than split tension test. Well, tensile strength split tension is related to modulus of rupture, and this is what it shows. If you can see or notice this, you see this is tensile strength is 1, modulus of rupture is 2. It is 2 and this is, if they are equal you would have got a 45-degree line, but what actually getting is a vertical line. So therefore, vertical line with this slope this much slope, which means that actually modulus of rupture always over predicts the tensile strength, right. So let us see the other test which is most popular and commonly used, is called split tension test, and it would look like this. You have a cylindrical specimen or can be cube also, as we shall say later. So in this cylindrical specimen, you apply load along this direction through a simple plate sort of thing, and like in case of MOR test, we use specimens size is 10 centimeter by 10 centimeter by 50 centimeter, with 40 centimeter being the central portion, which where we apply the between the supports 40 centimeter. In this case, we use this dimension is usually 15 or 150 millimeter, that is 15 centimeter, and this length is usually 300 mm. So, 1:2 cylinder that we have been talking about, that is what we use, and apply load, a kind of a point load. This is a cross section, loading cross section, and we apply load here. So, if one can look into the stress in a small element there from theory of elasticity, we will come to that. So, when you apply load like this, what happens is this along this vertical diameter tensile stresses act, as shown here. Tensile stresses act, very little portion, it is tensile stresses acts here, and it splits along this direction, splits simply. This will become two pieces, something like this, one portion, and it splits into another portion. So, you will have a cylinder gets splitted when you apply load like this, and that is why you call it split cylinder test. This is also used for rocks, is also called sometimes Brazilian test or Brazilian split cylinder test, and has been very popular for concrete now for determination of tensile strength. Right. Now, let us look at the split test. This is the typical stress distribution across the diameter. This axis shows 0 to d. So, this is the diameter of the specimen, 0 to d, and if you look at it, this side beyond this point, beyond this point is a compression, we are calling it positive, and tension is negative. So, only over a small height you have compression acting, but majority of the section, which is about, you can see d by 12 or even less than d by 12 is where compression is acting on both sides, but majority of the portion it is actually tensile stresses is acting, and it is actually by and large uniform tensile stress. So, from theory of elasticity one can calculate out this uniform stress, and this stress, uniform stress, is given as 2p over pi l d, where P is the load that has been applied on the specimen. P is the load that has been applied onto the specimen, right, over a thin plate, over using a thin plate, basically usually a plastic sheet or something is through which the load is applied, a thin plate or thin sheet through which it is actually applied. So, tensile strength is given as, tensile strength therefore will be given as 2p maximum load that you can apply divided by pi l d. So, this stress, this is, you can see that this is 1 pi l d, minus 1, stress is, stress multiplied by pi l d by 2 p, that is equals to 1, which means stress is equals to 2p by pi l d. So, it is nearly constant at 2p over pi l d, and you can calculate out the tensile strength from this value. You can calculate out the tensile strength from this value. So, this is what is called split tension test. It can be done on cubes also. IS 500 and IS 516 allows you to do it on cubes, or any other code allows you to do it on cubes, and this is how it is applied on a cube as well. And the formula here is of course slightly different. It is twice p by pi d square, because we are calling this as d, this dimension as d. So, it is 2p over pi d square, Again, this is validated from theory of elasticity, that you will have a tensile stresses here. Physically you can understand, when you are applying compressive load, it will have a tendency to go away, and just because the point load, just below the load there is a height, relatively higher tension, and since concrete fails in tension, this tension causes splitting of the either the cylinder or the cube, and you can find out the strength from this. Now, again let us compare these two tests. Least volume is subjected to maximum tension in modulus of rupture test, followed by split, followed by direct test. How it is? In modulus of rupture test, if you see the portion where tension is applied is the bottom portion, and even if you assume a stress diagram, you assume a stress diagram of this kind, So, maximum something like this, maximum tensile stress is here, all other portions tensile stress are not maximum, they are less, and the volume is only not even the half, half volume through which you are actually applying the tensile stress, bottom half, top half is in compression. So, volume of concrete which is subjected to tensile stress is in the central span, or where you have actually maximum bending moment, you have very little volume which is subjected to actually tensile stress, and that too only the bottom portion has got maximum, rest all are lesser than that. Now, you come to split you have split, say in case of split cylinder test, you have some portion where tensile stresses are acting, and this portion corresponds to about we have seen that this is d by about 12 on this side where it will not be acting, and d by 12 on this side on which it will be compressive, d by 12 on which it will be again compressive. So, you see the full section is again not subjected to direct tensile stress, whereas when you have a direct specimen, direct tensile stress, full section is subjected to direct tensile stress. So, maximum tension, volume is the least volume is subjected to maximum tension in MOR, followed by split, followed by direct, and this results in, this is the result why you have lower strength, that is MOR gives you higher value than split than the direct. Also we said earlier that non-uniform stress distribution in moment of in case of modulus of rupture test, in non-uniform stress distribution, because bottom has maximum, all other places it is less. So, it is non-uniform stress distribution in case of modulus of rupture, where the maximum tensile stress, the bending tensile stress is at the bottom fiber. Other fibers above the bottom fibers, they are at lesser stress. This is what happens in case of bending. Physically we can understand this. When something is bending, the bottom fiber is elongated most, followed by possibly the next fiber above it, and so on so forth, and at the neutral axis the fiber is not at all elongated, and if we go beyond it above, the fibers are actually compressed. So, if you look at it, there is a non-uniform stress distribution in case of modulus of rupture test, the flexure test. Bottom is actually at maximum stress and the neutral axis is at no stress. In between the stress varies. We are assuming it varies linearly, although in actual failure condition it does not vary linearly, but in any case it is non-uniform distribution. So, since it is non-uniform distribution, also in case of split, only the central portion there is uniform distribution, other portion there is less, and this can impede the propagation of crack. So, when cracks are forming, the portions where stresses are less, they may not allow the crack to propagate, and therefore, together with the issues that least volume is subjected to maximum tension, all other points that we have mentioned so far, and that is all confirms that modulus of rupture, theoretically modulus of rupture should be greater than split tension tensile strength and then direct tensile strength, direct tension strength. Strength determined through direct test should be the least, strength determined to split is somewhat greater than that, and tensile strength determined to modulus of rupture is still greater than that. Right, few more points. Crushed aggregate exhibit better modulus of rupture than rounded aggregate because of bond, and moisture condition also has some influence. It is interesting, crushed aggregate, because of the bond, in case of modulus of rupture, the crack has to start from the bottom and then propagate upward. As the P increases, the load increases, the bending stresses increases, the bending moment increases and the bending stresses increases. The crack has to propagate from the bottom towards the center, the neutral axis upward. Now, here if the bond aggregate provides better bond, if the aggregate provides better bond, and then this crack cannot propagate, and it has been observed that the crushed aggregate shows better modulus of rupture value than the rounded aggregate. This may not be true for other tests. The moisture condition also has got some influence on modulus of rupture. Now, you remember when we talked about moisture, influence of moisture on compressive strength, we said the compressive strength actually reduces when its moisture content is high. In a saturated specimen, the strength will be lower than the dry specimen, and it has been attributed to dilation of the cohesion force, because moisture would get absorbed in the gel structure, in the gel spaces, and this will dilate. It will create distance between the gel, or interlayer distances will increase, resulting in lesser cohesion reduction in cohesion, and this reduction in cohesion results in lowering of the strength. So, moist specimen, in case of compressive strength of concrete, moist specimen shows lower apparent strength, whereas dry one shows higher. But in case of tensile strength, I mean we are talking of the flexural tensile strength, it shows higher. I made some passing remark in the last lecture when we were talking about the effect of moisture content on strength of concrete, compressive strength of concrete, but we see here it is other way around. And if you remember, we mentioned at that time as well that the tensile strength becomes, in case of dry, that tensile strength is lower. The reason is it actually causes some shrinkage cracks. So, initially already because of drying there will be some shrinkage cracks. So, when you start applying load, this shrinkage cracks will help. The possibly initiation of crack will may even start from such shrinkage cracks. Well, shrinkage cracks, also shrinkage may affect the interfacial transition zone. So, shrinkage cracks due to drying has been attributed to improvement in strength by moisture, by saturation. In case of compression, if a moist specimen shows lower strength, here a moist specimen shows modulus of rupture, moist specimen shows higher strength. That because a dry specimen will have some amount of shrinkage cracks, and that may lower down the strength result in modulus of rupture. But this influence is not seen in case of other two, that is direct tensile test and test for another is a split cylinder test. In split test we do not see this, and this diagram shows us this behavior. As we can see, you see in case of splitting test, both direct, wet and dry is shown by this line, and which is showing least, actually least compared to all three. Splitting, well, wet and dry both the same, but you can see there is a difference, and this difference of course increases as we go towards the highest strength concrete. 80 MPa concrete shows much higher difference compared to, let us say, 30 or 20 MPa, where difference is low. If you go to flexure, the modulus of rupture test, this is a modulus of rupture test. This is the dry specimen, and this is the wet specimen. This is the dry specimen, this is the wet specimen, and wet specimen shows higher strength, and it is parallel. These two are parallel, and of course these two are much higher than both of them. So, and this differences also increases with either of this as the strength increases. So, these strengths are higher. The strengths are higher, and wet shows higher compared to dry, and this distance is more or less same irrespective of the strength. And this difference has been attributed to shrinkage of concrete due to drying. So, when you dry, shrinkage takes place, resulting in some shrinkage cracks at various places, including the interfacial transition zone, and that is why the strength is lower. So, that is what it is, the influence of moisture, and also aggregate do influence the strength of the aggregate do influence the strength of the aggregates also influence the strength of the concrete. Okay. Now, if we look at the relationship of Fc with Ft, if we look at the relationship of Fc with Ft, that is compressive strength with tensile strength, we said that there should exist a relationship between Fc and Ft, because we have seen in the failure envelope of under biaxial stresses in case of concrete, the compression and compressive strength is 8 times that of tensile strength. So, there must be some relationship existing between the two. So, empirical relationship has been attempted, and compressive strength versus flexural strength, something like this sort of relationship has been observed. And if one looks into a more elaborate diagram, one would see that in case of splitting tension test, these are the results, much more actually, so many test data for various size of aggregate, for various MSA, right, and this is the modulus of rupture test, and this is a split tension test. For this diagram is for split tension test, and this is a modulus of rupture test for various kind of aggregate size, etc., MSA, various MSA, these values are given, and modulus of rupture again shows lower value, modulus of rupture again shows higher value, split tension test shows lower value. So, relationship do exist between FCE and FT, because this is compressive strength FC and this is FT. So, there is a relationship exists between both FC and FT in flexure as well as direct split, as well as the split tension test. However, for our design purposes we cannot distinguish all that, because we have to use one of them. So, in case of design we use a specific value which has been given in code. There are several sort of relationships are available. In fact, several factors affect this relationship. These factors are something like aggregate type, age, curing condition, water cement ratio. So, various sort of even some sort of relatively more elaborate relationship has been suggested, but in the research level, of course, in the codal level, a simple relationships, or most of the codes adopt fairly simple relationship at the moment, simply relates the compressive strength to the tensile strength through formula, something of this kind. FT is proportional, FT is related to K, FC, where this is compressive strength, the power N, and this is a this F stands for strength, this is tensile strength, this is compressive strength. So, tensile strength is related to some constant multiplied by compressive strength to the power some N, and if you look at it, the IS code values, IS code gives you this value equals to, this K is taken as 0.7 and N is taken as 0.5 when FC and FT both are in MPa, when both are in MPa. In IS code, of course, all this this is when both of these are in MPa, FC and FT in MPa, then K is 0.7 and N is equals to 0.5. So, this is the value 0.5, that is the value suggested by the code for design purposes. Other codes also suggest similar values and similar sort of relationship, although there can be more elaborate relationship based on water cement ratio, curing condition, age and aggregate type, because we have seen that aggregate type may affect this, it does affect this relationship depending upon what relationship you are talking about. Right. So, this is the design relationship irrespective of how you measure what you have done. For design purposes, for calculation purposes, this is what is used. So, this is the idea regarding tensile strength of concrete. Let us look into now what is called fatigue. What is fatigue? Well, in case of concrete, we will define it in two different ways later on, but in general first define. When we have repeated loading, material fails at load lower than the static strength. The failure load being lower with number of repetitions. For example, supposing I have a load, I repeat go, I start from a load and increase the load and bring it down. So, I go cyclically apply the load. Somewhere I go up and go down, say 0 to some load and something like this. So, I repeat this load cyclically, go up and go down in any manner, I go up and go down. Now, what I will find it, after certain repetitions the specimen or the material will fail, but if I applied, let us say static load, then in one cycle it fails. Static load, one cycle it failed, and that is what is static strength. Static strength, that is what we call it, static ultimate strength. Now, if I apply repeated loading, then after certain number of repeated loading the material will fail, and at that time the load need not be the ultimate load, it can be lower. So, this load required to fail the material depends upon the number of cycles I have applied. More the number of cycles, it will fail at lesser and lesser load. There is a relationship. There is a relationship called SN relationship, strength versus number of cycle relationship. So, more the number of cycles, it will fail at much lesser load, this value at lower of this, lesser of this value. Now, this sort of a situation is referred to as fatigue failure. When you have repetitive loading, it need not, even if you do not go to the ultimate static failure load, if you are operating at a somewhat lower load and you repeat, go to that load, come back, zero it or go even negative, whatever it is, you repeat cyclically, you go increase the load, come back, increase the load and come back, you will find that the material fails, even though you have never reached the static ultimate failure load. This is the phenomena of fatigue. But in concrete, of course, there's something else also happen, we shall see just in few minutes time. So, that is called fatigue failure. Now, steel has a fixed endurance limit. An endurance limit is that many number of cycles, beyond which if you go on increasing the number of cycle, the fatigue load would not, or fatigue strength would not reduce. So, that is called endurance limit. Repetition beyond which the fatigue strength remains constant. We shall see through a diagram the same thing, but concrete does not have a fixed endurance limit, right. It does not have a fixed endurance limit. So, let us see this through a figure, maybe this will make things or more clear. Something like this, here on this side is the number of cycles, this is called an SN curve, right. This N is the number of cycle, it is usually plotted in log scale, and this is the strength, but we are talking in terms of ratio of fatigue strength to short term static strength. Static strength is when you have just applied the load once and it has failed. So, that I call a static strength, and this is 1. 1 is a is like one cycle, this will be 1, but when you have cycle increasing, then you have lesser values. So, fatigue, this is the ratio of fatigue strength to static strength, and you can see in case of steel, in case of mild steel, this decreases as I increase the number of repetition, number of cycles, but a point comes beyond which it does not decrease further. So, this point is nothing but the endurance limit, and we have a fixed endurance limit, clear cut defined, well defined endurance limit in case of mild steel, which is about, which will give you a fatigue strength of about 0.5 of the static strength. So, it is 50% of the static strength, right. So, if you expect fatigue load in case of your structure, you can actually reduce down your static strength by some value in which you should be operating, of course, depending upon the situation. Now, you look to concrete in tension, it is something like this, and there is no sign of anywhere actually there is an endurance limit, and in compression also it reduces down, and fatigue compressive strength would be somewhat this. So, what we do? We define it with respect to 1 million cycle, 10 to the power 6 cycles. So, what we say, fatigue compressive strength of concrete is defined with respect to 1 million cycle, that is the strength which it can withstand after 1 million cycle. If you have the n is equals to 10 to the power 6, the corresponding strength S, what we call as a fatigue compressive strength. Fatigue tensile strength is similarly defined as the same 1 million cycle. So, when you have 1 million cycle, the strength that it can actually withstand, that is what is a fatigue tensile strength. Alright. So, this is what we have in case of concrete when we apply cyclic or repetitive loading. Now, in concrete I said that there can be two types of fatigue behavior, one is sustained load. It is not need not be a repetitive loading, but you have sustained load near the static strength under increasing load, and this causes failure. A very slow rate of loading, you have just apply load near the static strength, and its failure. So, this is called static fatigue or creep rupture. This is a special thing to concrete, we call it creep rupture or static fatigue. Now, you see, fatigue is nothing but you are applying repetitive load. So, when you apply this repetitive load at a very slow rate, very slow rate, now such that frequency of application, cycles per second, is very small, very small. So, then such very slow rate of loading, that situation shows you static. That situation shows you what is called static fatigue or creep rupture. The other case I just mentioned was repeated cyclic loading or simple fatigue, as we understand. This is static fatigue. This diagram shows you static fatigue. For example, normal rate of loading, as we know that 140 kg per centimeter square per minute, that is what about 3 minutes we go to failure, and this is about ultimate short term strength. But if I go at a faster rate, very faster rate, I will get still higher strength. But if I slow down this rate, I have reached the ultimate short term strength, in 2 minutes, then my strength reduces. I still reduce it down. In 3 days, I fail the specimen and I reach here. And if I do the same thing in 50 days, I will reach there. So, increasing the test duration, right, that is decreasing the rate of loading, results in this kind of a failure. Failure at the strain increases, failure, the stress strain curve, actually this side is the strain and this side is the strength, or rather strength to strength to strength, stress to strength ratio. So, failure strain actually increases and your failure load therefore also reduces. So, you can see that this is in 50 days, if I try to fail it, I fail it, the failure strain is much higher now, much higher, and I have an envelope. This is called static fatigue failure envelope or crib rupture envelope. So, this is the envelope. If you increase it still further more days, it does not increase beyond that, it will be the failure strain, failure strain might increase, but the load does not increase. So, this is the envelope. So, as you go on increasing the duration, test duration, it fails at lower load, somewhat lower load, somewhere around 0.75, 75 of the actually 0.75 of the normal short term static strength, and if you increase the rate of loading, then it fails at much higher load. So, this is what we call it. In other words, it's you are applying the load once in 50 days in this case, once in 3 days, once in 2 minutes, once in 3 minutes, etc., etc. So, this is static fatigue behavior of concrete, and there are similar curve of the similar kind, which you can see that when we have again, supposing I subject the concrete specimen to 0.3 of the static strength and just keep it for a long period of time, what I will find out, after 30 years the strain will be increased like this. So, this is the limiting strength. After 30 years, beyond that there is no increase in strength. Similarly, if I load it to 0.6 of the static strength, I get something like this, the strain after 30 years, and so on and so forth, and it matches, this static fatigue failure envelope matches the strain. So, the strain that concrete specimen attains depends upon the load, and this envelope seems to match again. So, this also gives us static fatigue failure envelope, with respect to usual short term strength. So, static fatigue failure is actually very slow rate of loading. We find that at a very slow rate of loading, you apply load once in very long time, and you find that it fails at much lower load. So, this is something due to creep phenomena which is occurring. In fact, creep is very closely related to fatigue in case of concrete. I mentioned to you creep sometime in one of the previous lectures, that creep is the time dependent deformation. You keep the load, deformation will increase. So, that is what is the phenomena is creep, and this is related to the static fatigue is related to creep phenomena, and even in general creep of concrete, even cyclic creep can be cyclic fatigue can be related to secondary creep phenomena of concrete. So, this is right, this is static fatigue. Now, let us see cyclic fatigue. You see, if you apply load, repetitive load to the concrete specimen, then what will happen? You apply, go to that place, that is maximum, not the maximum load, but some load, some MPa, maybe some percentage of your static strength, ultimate strength, and release the load, it does not come back to its original position. That is because a lot of cracking, micro cracking takes place in concrete. We shall see that later on again when we look into the stress strain diagram of concrete. micro cracking occurs and which will not close down. So, therefore, there is certain amount of energy lost in creating those new surfaces, certain amount of strain energy has been absorbed there. So, it does not come back. Now, there is a hysteresis as we call it, and then again if I go on repeating after 675 cycle, I will find that hysteresis is relatively, hysteresis is is reduced, hysteresis has reduced, right. So, alternating load will have hysteresis, 675 I will have hysteresis, and if I go on increasing further, I find this area between the hysteresis loss, the energy lost in the hysteresis is less, because this was larger area, this is smaller area and this is still smaller area, smaller areas actually. So, after 24,000 cycles you find the hysteresis is very, very minimal. But you go on increasing this number of cycles, and strain also increases, of course, permanent strains, there will be some permanent strains here. So, strain increases, and here the strain starts increasing at a very faster rate, and hysteresis also starts increasing before failure. So, this dark line shows increasing load, this one shows the return load. So, there is hysteresis losses, and hysteresis losses reduces with number of cycles, but near the failure when large number of cycles have been applied, the hysteresis loss would become higher and strains will increase at a very, very faster rate, strains increases at a very faster rate. So, that is the behavior of fatigue behavior, fatigue behavior of concrete. Now, what kind of load it can withstand is under fatigue is given by what is known modified Goodman's diagram, So, that shows the range of stress to cause failure after 1,000,000 cycle, that is what is called, that is what is fatigue behavior, because we have defined the fatigue strength of concrete with respect to 1,000,000 cycle, because we do not have a specific endurance limit. So, we have defined it with respect to 1,000,000 cycle, the load or the load which under repetitive loading it can withstand for 1,000,000 cycle, that is what we call as fatigue strength of concrete. So, this modified Goodman's diagram gives you various cases. For example, this line it starts from this 45-degree line, which is the baseline, 45-degree line. 45-degree line is the baseline, this is the baseline actually, and this line represents this point, beyond this point it represents the minimum tensile stress, this represents the maximum compressive stress, right, line. And this line represents uniaxial tension, this line represents uniaxial tension and compression, and this line represents flexural tension and compression. This is uniaxial compression. Now, let us see how this diagram is read. For example, you will have as your cyclic loading would be always based upon a static loading. So, you will have some initial stress, over that the cyclic loading will be applied. Where this fatigue loading is important, like bridges, where there is a static load and over it there is some amount of cyclic load comes, or similar many other structures where repetitive load can come, say offshore structures or many other structures, where in offshore structures wave can come and hit repeatedly, but you have repeatedly, but you have a static stress already, repeated load or the cyclic load gets superimposed over it. So, Goodman's diagram deals with such situation. Say case A, you consider the A is this line, you have some amount of static stress which is tensile, because this side is a tension and this side is a compression. So, already nearly about 0.1 tensile stress is existing. Then from that, if you apply further uniaxial tension, you can go up to this line represents the limits of uniaxial tension. So, it touches here, this is the minimum tensile stress line. So, 0.1 0.1 you just draw a line. So, this is the minimum stress line. From here it can, if you are trying to find out how much is the cyclic tensile load or fatigue strength it will have in terms of tension load, this would be given by this. For example, if this was 0.2 of the ultimate tensile load if you have applied, then this much you could have gone under fatigue. The superimposed fatigue cyclic load would be this much. The range, this range is 0.5 in this particular case. Supposing you had 0.2 here and you could have gone here. So, this would have been again 0.4 or maybe slightly less than 0.4 or something of that kind. So, you could have gone up to 0.4. Over 0.2 you can apply still cyclically 0.4 tension 0.4 of the static strength, and that is the fatigue load. So this part of the, through this, this is the minimum tensile stress. So minimum tensile stress here is 0.1, and under uniaxial tension you can go to this line. This line is the maximum limit, that gives you the maximum limit. That means you can have, when you have an initial stress of 0.1, 10% of the ultimate tensile strength, then you can go to about 0.6 of the ultimate tensile strength repeatedly for 10 to the power 6 number of cycles, then it will fail. Only after 10 to the power 6 number of cycles it will fail. So you can see that how I use this, how one uses this graph. Similarly, you go to B, line B. Now this is for maximum compressive stress that has been applied. Now this is the maximum compressive stress that has been applied, right. Now from this, if I want to go to the uniaxial tension and compression, this compressive stress that has been applied. Now from this I want to go to uniaxial tension, that means I am reversing. I am reversing the stresses, right. I am reversing the stresses. So I can reverse the stress to about 0.5. I can reverse the compression, reverse this stress to 0.4 or 0.5, whatever it is, 0.4 or so, and this repetition can take place for 10 to the power 6 cycles before failure. Similarly, look at C, flexural compression. C starts from here, C is this line, right. So flexural compression is flexural tension and compression is this curve. So C is here, from here I can go up to this, and I can cycle this for 10 to the power 6. So this is 0.1 here, from where 1 to flexural compression I can go to this value, and I can cycle this for 10 to the power 6 number of cycles before failure. So if I want to find out how much I can apply the stress, this I can find out from Goodman's diagram. So look at D, uniaxial compression and uniaxial compression. So its starting point is here, uniaxial compression in this curve, uniaxial compression curve, and I can go to maximum compression this much. That means I can cycle over this portion. I can start from 0.1, this is nearly about 0.1, and go to about 0.5 or so, 0.5 or so. So therefore a range is 0.4. You see, the range is 0.4. So I can cycle over this. So using Goodman's diagram, I can actually Goodman's diagram, I can find out what is the fatigue strength of concrete. So modified Goodman's diagram is used in this manner. Next one is impact strength. Well, this is another issue, important one, impact strength of concrete. It has been observed that lower the water cement ratio, impact strength depends upon aggregate type. A strong aggregate would obviously show higher impact. For example, some sort of angular aggregate, this is granite, this is gravel. So it depends upon aggregate type. A stronger aggregate can absorb a lot of energy, and it can be, impact strength can be related to compressive strength. Number of, now how is this measured? Number of its rebound is applied, and number of rebound beyond which there will be no rebound, that is called is a measure of the impact strength, and this increases this increases with the compressive strength. Number of rebound required to come to no rebound situation. So that's an impact strength. Lower MSA improves impact strength, lower water for water stored concrete, this value is lowered when you have water stored in water, but if it is dry it is somewhat higher. All right, and then next we can look into the last aspect of this. Impact is nothing but actually means of very fast rate of loading. So when you have very fast rate of loading, the impact strength is generally higher than the compressive strength, that one can understand. So rate of loading when it is very high, that corresponds to impact strength, and actually strength can be 200% higher, right. Last is the abrasion resistance, and this also can be related to the compressive strength of concrete. You see, and as the water cement ratio decreases, the powder that is formed under grinding, that is a measure of abrasion. There are 3 different tests, and all tests, like one test is you have discs in which you grind, and then the powder that is formed under grinding, that is called that is a measure of impact resistance. Higher powder forms means lower the impact resistance. So as you increase the water cement ratio, impact resistance reduces, right. Last is the bond strength, and bond strength of concrete again can be related to compressive strength like this, bond strength of concrete can be related to compressive strength like this. In this manner you can relate it to the compressive strength, like higher the compressive strength, bond strength increases. This for plain bars, this for deformed bars. So summarizing the whole thing, we have looked into the tensile strength, fatigue strength, impact resistance, bond strength of concrete. This impact and resistance and bond strength, there is not much, the factors affecting are not understood. However, they can all be related to tensile strength of, compression strength of concrete. So almost all other strength properties of concrete can be related to compressive strength, and that is what I think. With that we can summarize